Okay, we're going to be going over our L'Hopital's rules homework. Okay, so for number 1, and again, we do have to look for that particular pattern. For this one, if we do substitute in our 2, we do have 0 over 0, and we really don't want to do any kind of derivative with this. However, what we can do is look at a chart, and if we're approaching 2 from the right, then what we can do is substitute in maybe something a little bit bigger than 2, and we do that. We have the absolute value of 2.1 minus 2 over 2.1 minus 2, and that's going to give us 1. And if we continue this, we're going to see that we will always generate a positive 1 with this. And we had a good review about this is slid over to 2. And here we do have that point where it doesn't work, but everything else to the right of 2 is going to generate a positive 1, and then everything to the left of 2 is going to generate a negative 1. So it's a good idea to learn this graph if we can. And so the answer to this limit is 1. Over on number 2, if we go through and substitute in, we're going to have 0 over 0 minus 1 minus e to the 0. And so that looks like we're going to generate 0 over 0. And so we do need to do L'Hopital's rule. And so from that, we have the limit as x approaches 0. And in the numerator, when I do the derivative, that's 1. Denominator is going to be 1 minus 0 minus e to the x. And so here we're going to get 1 over 1 minus, and then we have negative e to the 0. So that looks like we're going to generate 1/2. Okay, so again, we are going to substitute in 5 on this one. And when we do that, we are going to get 0 over 0. So we definitely have our indeterminate form. We are going to do L'Hopital's rule. And from that, we will do our derivative, limit as x approaches 5. And do remember, this is x minus 1 all raised to the 1/2 power. So when we do our rule here, we're going to have 1/2 times x minus 1 raised to the negative 1/2 times the derivative of the inside, which is just 1, and then minus 0. And then in the denominator, we're going to have 2x minus 0. Now let's go ahead and try to evaluate our limit again. And so we're going to have 1/2 times 4 to the negative 1/2, and that's going to be over 10. And so we're going to end up with 1/2 times 1/2, because here the square root of 4 is 2, and the negative means reciprocal, over 10, so we end up with 1 over 40. Now number 4 is kind of misleading. You kind of want to think, plug in, and get L'Hopital's rule, but this one is really just looking at a power struggle between the numerator and denominator, and that's because we have a polynomial over a polynomial. So if we look at our power struggle with 3x to the 4th over 2x to the 5th, we are larger in the denominator, so that means that this is going to tend toward 0. Okay, so for number 5, here we're going to go through and we substitute in our infinity. We are going to end up with an infinity over infinity, which will say, hey, L'Hopital's rule, but this being x squared inside the radical, that's going to make a mess of L'Hopital's rule, and you're really just going to go in a continuous cycle. So we have to do some theory here and think about, as x values grow infinitely large, this plus 3 is really not going to be as dominant as x increases in value. What is going to be dominant is going to be the square root of x squared. And then in the bottom, the only power we have is x. If we do the square root of x squared, that is the absolute value of x back over x. And again, that's right back to our very first problem where we had this graph. Now, of course, it was shifted to the right too, but it's still the same concept there. So as x is approaching infinity, then we can say this limit is approaching 1. Okay, over on the next one, if we substitute in 3, we will get 0 over 0. And so, again, we need L'Hopital's rule. And so we're going to have the limit as x approaches 3. And in the numerator, we have 2x. And in the denominator, great review here, the derivative of the natural log of x minus 2, it's going to be the derivative of x minus 2 over x minus 2. And I wouldn't try to figure all this out until I plugged in my 3. So if I do that, I'm going to have 6 over 1 over 1. Well, that's nice. That just turns out to be 6. Okay, so for number 7, again, we do our substitution, and we're going to get sine of pi, which is 0, and cosine of pi over 2 is 0. So we do need L'Hopital again. And so we're going to look at our limit as theta approaches pi over 2. And we're going to do the derivative of sine of an angle is cosine of that same angle times the derivative of the angle. And then the same process in the bottom, derivative of cosine is going to be negative sine of the angle times the derivative of that angle. And now we're going to substitute in. And when we do our substitution here, we are going to get cosine of pi, because the 2's will cancel, times 2 over negative sine of pi over 2 times 1. So that's going to give me 2 over negative 1. So it looks like, oh no, that's going to be negative 2 over negative 1, which is positive 2. Okay, so number 8, again, substituting in our 0, we're going to get 0 over 0. We do need to do our L'Hopital's rule. And when we do that, again, we're going to have the limit as theta approaches 0. And derivative of cosine is going to be negative sine of that angle, which is theta plus pi over 2, times the derivative of the angle. Pi over 2 is a number, so that's going to go to 0. And derivative of theta is just 1. Over derivative of sine is going to be cosine of theta. Now when we do our substitution here, we are going to get negative 1 in the numerator and positive 1 in the denominator. So we get 1 over 1 or negative 1. I didn't write. All right, so for number 9, if we substitute in for here, let's see, we're going to get infinity minus cosine of infinity. That one doesn't exist because cosine is oscillating. Remember, cosine looks like this. So it's not approaching a specific value over infinity. So don't know what that is. That's a mess. And so what we need to do is divide this up. So we're going to have the limit as x approaches infinity. And I'm going to divide this up and say x over x minus cosine of x over x. And so that's going to give me the limit as x approaches infinity of 1 minus cosine x over x. And then that's going to generate a 1 minus, and if we look at our rates, that's going to oscillate. It's never going to be bigger than 1 or smaller than negative 1. However, this is going to grow infinitely huge, so it's going to be 1 minus 0 or 1. All right, so number 10, starting out, I would go ahead, that negative exponent there is awful suspicious looking, and so we're going to go ahead and take care of it. Remember, negative exponents mean for you to move it. And so if we look at this now, looking at our rates of growth, that would be a good idea to look at because we are heading toward infinity. And in my mind, I'm thinking this will probably end up being 0 because this grows very slowly. and this one is very fast. And so eventually this is going to overpower this one, and that should tend towards 0. Now let's look at it, that because if we just substitute in infinity, then we are going to get infinity over infinity, because that's where they're both approaching, and that does imply L'Hopital's rule. And so if we do that, we're going to look at our limit as x approaches infinity, and the derivative of natural log of x is going to be 1 over x. Derivative of e to the x is e to the x. And so we have the limit as x approaches infinity of 1 over x times e to the x. And we do see that that does tend towards 0. Okay, so now let's look at number 11. And with this one, we can look at, if we substitute in negative infinity, then we have the idea that we're going to have negative infinity times, and let's talk about our graph of tangent, because x is approaching negative infinity. The graph of tangent kind of looks like the graph of x cubed. Looks something like this, but tangent is periodical and it does repeat itself. And if we remember from the unit circle, tangent does not exist at pi over 2. And so if this just repeats itself, that's going to be negative pi over 2 and so forth. So notice that as x approaches negative infinity, then I can look at this limit as x approaches negative infinity of inverse tangent x. Well, graphically, we see that this is tending toward here. If I'm going toward negative infinity, then here this graph is itself is getting closer and closer and closer to negative pi over 2. Now it's not going to be equal to it, but it sure is getting closer and closer there. And again, we're looking at tangent. This inverse says tangent of what angle equals does not exist, is really what that's saying. It's shooting off toward infinity here. So that is going to be our negative pi over 2. So looking at this, we've got a negative infinity from our x times our negative pi over 2 from our inverse tangent. And so it looks like that this limit then, that product, as x approaches negative infinity of x times inverse tangent x, it looks like that's going to tend toward positive infinity. Now, if we would want to look at our rates of growth, the only thing that inverse tangent is contributing to the situation would be at this negative pi over 2, or really the negative is what's the important part there. All right, let's look at number 12. And number 12, very similar. So again, we have x here is approaching 0. So if I substitute that in, again, this is saying sine of what angle gives me 0. And we know that that is, or we should know, sine of 0 is 0. So this is going to give me 0 over 0. Well, that's nice. We can do our L'Hopital's rule, and this is a great review of derivative of the inverse. As x approaches infinity, the derivative of the inverse sine, it was a formula. It's 1 over the square root of 1 minus x squared. That's just our formula. We developed it last year, and we can develop it again as needed. Over derivative of x is 1. So here, when we substitute in and do our limit, we get 1 over 1, which is 1. Okay, these next couple of limits, those are going to be like the ones where we come up with our famous limit with e. So let's see if we can't trudge through it. It's great practice. We have the time in class. We can go through this. If we do apply our limit, we do need to keep in mind, let's see, as we approach negative 1, a natural log of x, just a quick reminder of what that graph looks like. Natural log of x looks something like this, and it does flatten out. And right here where it crosses the x-axis, it crosses at 1, 0. So if I substitute in a 1, even if you're coming in from the left side here, you're going to get 0 raised to the 0. And keep in mind that is calculus. And so what's given us 0 raised to the 0 is this part here. So that's why we kind of do a substitution with this. We're going to say let y equal 1 minus x to the natural log of x. And then we're going to go ahead and we're going to do the natural log of both sides. And again, the whole point of that is so that we can bring down this exponent and say times natural log of 1 minus x. That's the whole point of this. Now, if we go ahead and look at our limit as x approaches 1, so we're going to say our limit as x approaches 1 from the left of the natural log of y, well, look at what we're going to get. We're going to have natural log of 1, which is 0, times, and if we plug in 1 here, natural log of this, that's going to shoot down toward infinity. So we do kind of have a form that we need to work with. We need to get this to be a ratio, so we can do that. We can take and see where this part right here, let's rewrite that. And that's where it gets to be a little tedious with this. We have the natural log of 1 minus x over, and I'm going to put this 1 over natural log of x. And when we do that, then we see that we're going to have infinity over infinity. So that changes things a bit. And if we have that, then we qualify for L'Hopital's rule. And so let's see what happens there. And again, we'll look at our limit as x is approaching 1 from the left. And we do our derivative. So we're going to have negative 1 over 1 minus x. And then all of that is over. And goodness, we can flip this over and write that to be natural log of x raised to the negative 1. So if I do that, that's going to be negative times natural log of x to the negative 2 times the derivative of the inside, which is going to give us 1 over x. All right, now let's see. If we do L'Hopital's rule again, looks like we're still going to have a mess. We are. So, oh goodness, we're going to have to do, it looks like L'Hopital's rule yet again. It looks like we've got a mess here. Yep. And so let's go through L'Hopital's rule one more time. Before I do L'Hopital's rule again, I think I might clear some of this up. Let's see. We have some negatives here that we can cancel out for sure. And I might go ahead and flip that 1 over x up to the top. Let's see what we've got. Let's put that limit on hold for just a minute. Let's go ahead and make our positive. We have 1 over 1 minus x. And this down here, that's 1 over the natural log of x all squared times 1 over x. So that looks like all of that's going to be over 1 over x times natural log of x all squared. Okay, and so here we're going to do our keep change flip. So we have 1 over 1 minus x times, and we're going to flip this over and have x times natural log of x all squared over 1. And let's see, what is that going to generate for us? We're going to have x times natural log of x all squared over 1 minus x. And again, we're going to have 0 over 0, so we're going to have to do L'Hopital's rule again. And if we do L'Hopital's rule again, let's see. In the numerator, we are approaching 1. In the denominator, we're going to end up here. This is all going to be over 1 for sure. And notice in the top here, if we go ahead and go back through this, we're still going to have a natural log involved in this. And we know the natural log of 1 is 0. So all of that's going to go to 0. We can go through that mess again, but it's going to head towards 0. Now, it would be great if we were finished, but however, we are not. What we were able to do is go through and find this is going to be equal to 0. So I'm going to write that again because that's just going to be bad math if I write that there. And can't have that. The math people come out and arrest us. So we have the limit as x approaches 1 from the left, the natural log of y, and we saw all of that ended up being 0. And now we know that the natural log of y is going to be 0. And so from here we need to solve for y, and we say that y is going to be equal to e raised to the 0 power. Thus we get 1. That limit is 1. Okay, 14 again, same idea here as we go through this. We are going to get 0 raised to the 0 power. And again, this exponent is what's causing us issues. So we're going to let y equal e to the x minus 1 raised to the x. Just like the other problems, we're going to do the natural log of y equals, and I'm going to go ahead and move that down, and then times natural log of e to the x minus 1. All right, and so now if we do our limit as x approaches 0 from the right of x times natural log of e to the x minus 1, we are going to have a mess here. We still end up with having 0, looks like times infinity. So let's do our quotient. We can rewrite this to be our limit as x approaches 0 from the right of, and let's move our x to the bottom. So we're going to have the natural log of e to the x minus 1 over x to the negative 1. And yay, that is going to give us infinity over infinity again. So we're getting there. And now we need L'Hopital's rule. We are going to do that. And so if I do the derivative of the top, again, I have the limit as x approaches 0 from the right. The derivative of the natural log of e to the x is going to be e to the x over e to the x minus 1. And then all of that is over negative x to the negative 2. And once more, if we plug in our 0, we're going to get 0 over 0. Sweet goodness. And so now we're ready to go ahead and do L'Hopital's rule one more time. I would go ahead and clear up some of the fractions, though, on that. So let's go ahead and do that. And if we do clear up some of the fractions, let's see what we're going to get. Well, my pen stopped. We're going to have e to the x over e to the x minus 1. And this is negative 1 over x squared. So that's going to be x squared over negative 1. So we're going to have x squared e to the x. I'm going to have a negative there over e to the x minus 1. Alrighty, so now let's gear up L'Hopital again. So we're going to have the limit as x approaches 0 from the right, and the derivative of the top, we've got the quotient rule. So we have the first times the derivative of the second, plus the second times the derivative of the first. And then in the bottom, derivative of e to the x is e to the x. And goodness, let's see, what is that? We have a common factor of e to the x, so I'm going to get rid of that. And if we plug in 0 there, all of that is going to tend towards 0. And so again, keep in mind that's not our answer though. Remember, that means that our limit as x approaches 0 from the right of the natural log of y equals 0. So the natural log of y equals 0, or e to the 0 equals y. So here our limit is 1. Okay, so for now, number 15, we are going to go through the same process again. And let's see, if we plug in 0 here, we're going to end up with 1 raised to the infinity, which again, we're tempted to say is 1, but we are in calculus, so we can't do that. Again, we need to move that exponent, so we're going to say y equals cosine of x, and all of that is raised to the 3 over x squared. Then we will do our natural log equals 3 over x squared, natural log of cosine of x. What a mess. And let's see, we can go through and do our limit again. I believe we're going to end up with a mess here. So again, we're going to go through and try to look at, we're going to have 3 natural log of cosine of x over x squared. And yeah, we're going to end up with, again, 0 over 0. So let's do L'Hopital. And we have our limit as x approaches 0. And in the numerator, if we do our derivative there, which is really strange, our 3 is just going to sit there. It's the coefficient. Derivative of cosine is negative sine of x over cosine x. And then in the bottom, it looks like we're going to get 2x. And here, if we plug in our 0, well, snot. We're going to get 0 over 0 again. So once again, we will do L'Hopital's rule. So we're going to have the limit as x approaches 0. And for that, I'm going to cheat. I'm going to move that negative out. And sine over cosine is tangent. And the derivative of tangent is secant squared. And so I'm going to have secant squared x over 2. Oh, that works out nice, because now that's going to be negative 3 times 1 over 2. So negative 3 halves. But wait, that's not our answer. We're coming back and saying, therefore, the limit as x approaches 0, the natural log of y, equals negative 3 halves. And so from here, we can say y equals e to the negative 3 halves. Okay, for our next problem, if we substitute in here and look at the graph of 1 over x and 1 over sine x, as we're approaching 0, we are ending up with infinity minus infinity, which is not 0. But when we're in this form, that means we need to get this together and get a least common denominator and change this form a bit. And for this, we're going to say 1 times sine x minus x times 1 all over x sine x. And again, if we go through, we are going to get 0 over 0. So now let's do L'Hopital's rule. And we have the limit as x approaches 0 from the left of cosine x minus 1 over the first times derivative of the second plus second times derivative of the first. And if we substitute in a 0 here, of course, we're going to get 1 minus 1 over 0. So, yay, let's do L'Hopital's rule one more awesome time. And so derivative of cosine negative sine x over, oh dear, well, let's see, down there we have the product rule. So we have the first times derivative of the second plus second times derivative of the first, and then we have plus derivative here is going to be cosine x. So it looks like if we substitute in a 0, we're going to get a 0 over looks like a 2, so all of that's going to go to 0. But again, that is not the final answer. We know that really, hopefully y'all are seeing, that just implies the limit is e to the 0, which in this case, oh wait, no. I got caught in a routine, guys. That is your final answer. No. I have lost my marbles. Nope. So that is your final answer. We did not have to do the ln, so the limit here is 0. All right, so one of the things that I was talking about earlier, if we can look at our growth rates as x approaches infinity, we can do some pretty good decision making with our limits, as long as we are paying attention to the functions we're dealing with. Also, this whole idea of growth rate is very important when we go on into our subject matter with talking about convergence and divergence. So please keep in mind these rates. So here it wanted us to rank the following functions in order of growth rate as x approaches infinity from slowest to fastest. So looking at all of those, the slowest growth rate would be y equals 3, because that's constant. It is not increasing in value at all. So the next one that we have to look at would be y equals x, or y equals natural log of x. Well, the graph of y equals x is a line, nice, friendly line there. However, natural log of x, though, if we remember that graph, it looks something like this. And so if we start talking about growth rates, notice that y equals natural log of x is going to grow almost as slow as a constant value. So that is something to keep in mind. And then, of course, we would put y equals x next. And then thinking about the graphs, of course, y equals x squared. And then, of course, y equals, what was the next one they gave us? X to the 8th. And then usually the fastest growing is going to be this exponential here, e to the x. Remember, e to the x, if I put that up here on our other graphs to help us remember, e to the x was an exponential function that grew something like this. So we see that in behavior how fast those are growing. Now we're going to use this to do number 18. Here we're just going to use the idea of relative growth to see, and this is almost like a power struggle is what we're looking at here. So if we keep that power struggle in mind, that is indeed what we're looking for, number one, hopefully we see that this turns out to be 0. And the reason why is the natural log of x grows slower than y equals x. And so eventually y equals x is going to outrun our natural log of x. Okay, looking at this one, if we substitute in this negative infinity here, that's going to move that term. So in other words, if I have negative big, but then that's going to be times e to the negative big, and we just saw e is a very fast growing function, then here we need to do some rearranging with this as x approaches. Again, if I move that, then it's really going to be towards positive infinity. But here's what I want y'all to think about is really this is going to be x over an e to the x, because you're approaching that negative infinity. So which one is going to grow faster? Well, of course, e to the x does. So this limit is going to tend toward 0. Our next one, natural log of x over x to the 4th plus e to the x. As x grows increasingly large, really this x to the 4th isn't going to play as much of a part as e to the x. And so if we have a slow growing function over a fast growing function, then we know that's going to tend toward 0. And then here on part D, again, we've got e to the x, which is like Superman. And then we've got, I guess, Robin over here, minus x. And then that e to the x is going to overtake minus x. But then x squared is never going to grow at the same rate as e to the x. So e to the x is going to overcome all of that, and so it's going to go toward infinity.